Okay, so we have practiced conservation of energy using many problems. Now we're gonna see some problems with elastic potential energy. We haven't done any problems with elastic potential energy. Now we're gonna use some questions to practice that term. Let's take a look at the question on slide 10, the same PowerPoint, slide 10. In this question, there will be elastic potential energy we need to consider. The launching mechanism of a pop gun consists of trigger released spring, okay? The spring is compressed 17 centimeters to position A, and then the trigger is fired. Projectile rises up, leaves the spring at position B, and then reaches the maximum height at position C. If the spring constant is 350 newtons per meter, find the height of C relative to B. So first let's draw it out. So the spring is going to be first compressed 17 centimeters. Okay, and then the projectile is placed here, locked here. Okay, then once the pop gun is triggered, then the spring is going to be released, right? When it's released, it's just going to go back to its original length, right? So it's going to push this ball up. Okay, it's going to go back to its original length. So this is point B, the problem set. That's the original length. This is point A, and this distance we call it's 17 centimeters. Okay. Now, but remember the projectile is not attached to the spring, right? Otherwise, it's just going to stop here. You just place this projectile, the ball, on top of the spring, right? The spring pushes up, so it's going to go up. But after this point, the spring already back to its original length. The spring is not going to be moving anymore, right? So the spring after this point, the spring is going to be stationary, not moving at all. But the ball keeps going up, right? The ball now leaves the spring. It's going to leave the spring and then keep going up. Then only gravity is on it. So that's going to be free fall with the initial velocity. So it's going to keep going up until it reaches the highest point, C. And then it's going to drop, right? So after this point, it's just going to be free fall with the initial velocity. And we have seen that before. Let's see what we want to find. Find the height of C relative to B. So we just want to find this height. Right? We want to find this height. So if you say you know this velocity, initial velocity of this ball at this point, actually from B to C, we know how to solve that, right? That's just free fall with the initial velocity. I can use these kinematic equations if I know the initial velocity of this ball at this point. But how do I find the initial velocity? Well, okay, we have done some problems like this. When you break it into two processes, the initial values at this point is going to be the final values of the first process, right? So if I can use this process from A to B to find the values for the velocity of this ball at this point, then I can go ahead and use kinematic equations and then find the maximum height of C. Now let's take a look at the process from A to B. From A to B, that's really complicated because how many forces are on A when, how many forces are on this projectile when it's moving from A to B? Gravity is on it. Gravity is always on it, right? Now the spring has a force on it. Okay? So, and then we know the gravity, it's always m times g. The spring force, we also have an equation to calculate it. Right? So the magnitude is always going to be this, k times delta x. Remember, this delta x is the displacement from the equilibrium position. It doesn't have always to be in horizontal direction, okay? In this case, it's vertical, but it's still the displacement. Now, if I want to, you would say, well, I know these two equations. All I need to do is just plug these two numbers in and find these two forces, and then use Newton's second will find the acceleration, and then use the acceleration to find the final speed, right? Because I can call this initial final. But you should be careful. This is not a constant acceleration motion. because gravity is a constant. Yeah, sure, I know that. But this guy actually, the spring force is not a constant in this process from A to B, right? Because when the projectile goes from A to B, the displacement for the spring is actually going down, right? Because it's coming back to its original length. The displacement for the spring is going to be less and less until to 0, right? So the displacement actually changes from 17 centimeters to 0 at the end. So the force of the spring is not a constant. It actually decreases from some value to 0. So this is not a constant acceleration motion. You can't just do kinematics between A and B. So that looks like a rather complicated process. What do we do when we see a process that's rather complicated? We cannot apply Newton's laws and kinematic equations. We use conservation of energy, right? So let's use conservation of energy. And when I use the conservation of energy, I don't even need to break it into 2 different processes. Okay, that's the beauty of this law. Okay, I can just call this initial. Because as I said, the conservation of energy doesn't care how complicated this process is, right? You can go like this. The path of this object can be like this. Doesn't matter, right? I call this initial, I call this final. I apply conservation of energy. I need the values at initial and final. I do need to use this path maybe to calculate the work, okay? But it doesn't matter. I don't need to break it in different processes, okay? If I pick my initial there and that's fine. Final here, okay? There's nothing wrong. So what we can do is this. I'm going to call this point the A point initial. This is my initial point. And this is my final point. Okay, I don't even need to care that there are 2 processes. Okay, some people, they're afraid of doing that. No, don't be afraid of doing that. Okay, you can always apply conservation of energy in this whole process. Okay, as long as you can find all the initial values and final values you need and the work in this whole process. That's it. Okay, so now let's do that. If I use that as my initial and final, let's set up conservation of energy. Set up conservation of energy is always easy because the terms, they all have definitions, right? All you need to do is just use the definition and find these terms. So let's do this. Now owning this, the projectile is something I'm interested in. So the projectile is going to have an kinetic energy final minus initial. Gravitational potential energy is going to have a final and initial. Now we do have an elastic potential energy, so I'm not going to write a 0. I would write, what is the definition for elastic potential energy? 1/2 k delta x squared, right? So now I'm going to have delta x f squared minus delta xi squared equals external work. Okay, so now let's see. So the left-hand side, I'm going to figure out all these terms. But what about the right-hand side? How many terms do I have on the right-hand side? Let's take a look at the forces on this guy. Gravity, right? Gravity is going to be always on it from A to B to C. But you never need to worry about gravity on the right-hand side, right? So good. Elastic potential, spring force, there are only 2 forces on, right? Spring force, you also don't need to worry about it. Why? Because we also defined elastic potential energy. Whenever you define an elastic potential energy for a conservative force, you already include that force in your system. That's not considered a force from the outside. So you don't need to calculate external work using that force. Is this spring force still doing work? Yes, it is, right? I'm not saying that it's not doing work. It's still doing work, but it's some force in my system. I don't need to calculate the work on the right-hand side because I only need to calculate the work done from the outside on the system, right? The spring is in my system. The force is the force between the inside of my system. I don't need to calculate it. So spring force and gravity are very special forces. That's why we define them. We define potential energy for these 2 forces. So we never calculate work done by these 2 forces on the right-hand side. Very nice. And then That's it. There's no other force. Both of these two forces, they are in my system. I get a 0 on the right hand side because there's no work. There's even no force from the outside. There's no external force. For this whole process, right, and the spring force actually changes. Okay, so it's a very nice thing that we define the elastic potential energy. So I don't need to worry about the complicated behavior of this spring force, because you can still calculate the work done by the spring force. You just need to use calculus, right? But if I define elastic potential energy for this spring force, I only need to calculate these two terms, initial and final. It doesn't go to the right hand side. So that's a nice thing about this potential energy, okay? So in this whole process, no external work at all. So 0 on the right hand side. So all I need to do is just figure out the left hand side. Okay, there's 6 terms, okay? Again, as I said, in this class, we usually get many zeros when we use conservation energy. So let's see. I want to find the relative height of C relative to B, right? The height of C relative to B. So that's going to be the final height. So I'm going to leave the final height here, right? So that's going to be the final height I want to find. Now, these two terms, what is the initial speed of the projectile? Well, the projectile, everything is compressed and ready, right? And then the trigger is fired. So the initial speed of this projectile is definitely going to be 0. Remember, I'm still calling this was the 0. So initial speed of the projectile is 0. What is the final speed? Now I'm calling this the final point. I don't need to worry about B. I don't, because I'm considering this whole process. What is the final speed at point C? Oh, that's still 0 because it's at the top and it's only moving in y direction. It's not moving in x direction. So the VF is also going to be 0. We got rid of 2 terms, right? Isn't that nice? Okay, we got rid of 2 terms. So it turns out there's no change in the kinetic energy. If you just consider this whole process, initial, final, does the kinetic energy change at all in this whole process? Yes, it is changing. But if I only take a look at the initial and final points, these 2 numbers don't change, right? The value can still go from 0 to 5 and 2 and 3 and 4 and then back to 0. That's fine. I only need to have these 2 values and they're just 2 zeros, okay? I don't need to worry about how they change, how this value changes between these 2 points. No. Now these 2 terms, so the final height is what I'm looking for, so I'm going to leave it here. Initial height, okay? So if you say this is the final height, you are actually using this as your 0 reference. And this 0 reference is neither your final height nor your initial height, right? So this is just it's just a random point I pick as a 0 reference because the problem says, I want you to find the height of C relative to B. So I'm just going to call B 0, right? So that makes it easier. So if I call this as 0 height, what is the height of point A? That's going to be negative 17, right? That's what I said. If you pick a 0 reference, you're going to stick to the 0 reference. Any point lower than the 0 reference in y direction, you're going to call it negative height, right? Okay? So we will have negative height when people, they always try to interpret these words literally. Height. Height is always positive. What does negative height mean? Well, actually, we do have negative height in real life, right? Anything lower than ground, you still call it 0 height, right? When you go into an elevator, sometimes you see a level -1. Does that like freak you out? No, it just means it's the basement. It's lower than the ground floor, right? If you call the ground floor 0 or 1, that's lower than that, okay? So the initial height you plug in is going to be negative 17, okay? You don't plug in 17. You don't make negative and positive. You don't drop all the negative signs. You should always assign all the numbers with the correct signs. Don't be afraid of negative numbers. Negative signs, they are meaningful in physics. Okay, so that's the initial height. So you do have the initial height. That's not 0, because I'm not calling any of these 2 guys my 0 reference. I'm calling this point my 0 height. So you do have the initial height. What about these 2 numbers? So you're going to take a look at these 2 displacement. Only for the spring. So you only look at the spring. You don't look at the projectile. Okay. Some people they make that mistake. Okay. This two displacement is only for the spring. Okay. Now let's take a look at the spring. This is the initial point. Okay. So if this is a spring, where is the equilibrium point of the spring? That's point B, right? That's the original length. Okay. So it has nothing to do with this H0 height I just assumed, right? It has nothing to do with that. I only look at the spring. It's just that the P point is also the zero reference, the equilibrium point of the spring, okay? But these 2 points, they have nothing to do with each other, okay? So of course, the data xi I plug in is gonna be 17 centimeters, right? Some people may say, well, why don't we call it negative? You can call it negative, that's fine, but the square is going to take care of that, right? So that means this data x, if you have a spring, doesn't matter if it's compressed or stretched, you don't really need to worry about the sign, okay? You don't need to say, do I call this positive and this negative? You can do that if you like, but I always have a square at the end, so I'm just going to use the difference, right? If this is the original length, this is the displacement. This is a displacement, okay? So I don't need to worry about the sign when I work with the spring, okay? So that's easy. But when I work with the height, because I don't have a square here, so you will assign them the correct signs, okay? So the initial height for this point, it's gonna be this. So the final initial displacement for the spring, only for the spring, okay? Final point, this is the final point. Okay, but you only look at the spring, right? The spring is here, okay? So what is the displacement for the spring at the final point? Some people, they would use this. They say, oh, the project height has moved to the maximum height. But remember, these 2 terms, they're only for the spring. What is the displacement for the spring at this point when the ball has reached the maximum? The spring is already back to the original length. There is no displacement for the spring. Actually, after point B, there's no change for the spring. The displacement for the spring is always 0 after point B, right? Has nothing to do with the projectile, unless the problem says the projectile is attached to the spring, right? So it's gonna stretch the spring. But again, you're gonna draw it out, you're gonna see that. Okay, so in this case, it's not attached to it. The ball is on, the projectile is totally on its own after point B. So the final displacement for the spring, only for the spring, it's going to be 0. Okay, so for these 2 terms, you only look at the spring. Okay, that's a mistake people make. They will use the displacement for an object or something in the problem. No, you only look at spring. If the spring is already back to the original point, doesn't matter how the other objects are moving in the system, you only look at the spring. So you see that this term becomes 0. So how many terms are you left in this equation? You only have 3. We started with 6. We only have 3, right? And I'm trying to find, what do I want to find? I'm trying to find the final height. Okay, now you can go ahead and rearrange this equation, find the final height, because we already have all the numbers we need. Okay, pause the video, finish the algebra. What is the final height? You will get this, mghi plus 1/2 k data xi squared. You just divide both sides by mg. You will get the final height. But again, remember, what is the hi you plug in? Negative 0.17 meters, right? Okay? Because I assume B is a 0 reference. What is the final height you got? The final height I got is 1.30 meters. So this is the final height of this projectile relative to B, okay? So again, one thing we learned in this question is that if you set up a 0 reference, okay, for the height, any point lower than the 0 reference, you're going to assign a negative sign. Otherwise, you will get the wrong answer, okay? And then for the spring, the data x doesn't have to be always in x direction. It's just a symbol. It's a displacement of the spring from its original length, from the equilibrium point. And this data x has nothing to do with other objects. You only look at the spring to figure out the data x. Okay? If something is attached to the spring and it's moving, so it will have the spring moving with it, right? But again, once you draw it, you know everything. Okay? Sometimes it will be connected to another object if that object is attached to the spring. But if nothing is attached to it, then it's just the spring is on its own. Okay? All right, so we just finished this question. Let's take a look at the next one. Okay, so next one pretty much has everything we have learned. So this is a good exercise. Let's take a look at it. There are two blocks. I'm going to draw it out. Okay, so there's a spring here, and then attached to a wall, but then the other end is attached to a block M1, right? So that's what it says. But M1 is attached to M2 with the string, right? So there's a pulley here. And then that's the floor. Now let's see what's happening here. So M1 is on a rough surface. So and then the spring has a spring constant. So you know the K of the spring, right? And then you know there's a mu K, but oh, you're looking for mu K, so you don't have the mu K. You're trying to find the mu K. And then, okay, so you know that these two masses, when the spring is unstretched, M2 is released from rest. It falls a distance 0.3 meters before coming to a stop, okay? We want to find the coefficient of kinetic friction between M1 and M surface. So we want to find mu K, okay? So, the problem says M2 is released from rest. Okay, if you release M2 from rest, okay, it's going to start to fall. It's going to pull M1 to the right, right? So both of them are going to be moving. But the problem says it falls a distance 0.3 meters before coming to a stop. What does that mean? How come that M2 is going to come to a stop? Okay, because gravity is pulling it, right? But again, if you draw a Fibonacci diagram, okay, you're going to have M2G for M2 and then tension for M2. So if the tension, you see, if the tension gets larger and larger, it will stop M2. So initially, the tension is going to be smaller than M2G. So M2G is greater than GT, it's going to pull it down, right? But what if the tension changes, right? So let's take a look at M1. So M1 is going to have its own gravity, tension, normal force, okay, and then there's a friction force on it, okay, kinetic friction, and there's also a spring force on it. So there are 5 forces on it. So, okay, first of all, I know the gravity and the normal force, they will cancel, okay, for sure. But this tension, okay, so if this M2 is heavy enough, so you're going to first pull everything down, right? So tension at the first at the beginning, it's going to be greater than friction force, kinetic friction, and the spring force just starts from 0, right? So the beginning tension is going to be greater than these two guys. So it's going to start pulling M1 to the right. So if there's no spring, then nothing's going to change, right? The tension, the kinetic, so everything's going to be constant. But the spring force, remember, the magnitude of the spring force is always K times delta X. So the spring force is very interesting. When M1 moves to the right, so the displacement of the spring is, because now the spring is attached to M1, so it's going to move with M1, so it's going to be stretched. So this force is going to get larger and larger. Spring force is going to get larger and larger, right? If this spring force gets larger and larger, it's going to slow down M1. If M1 slows down, so M1 is going to slow down M2, right? So this tension is going to get larger at the end. So it's going to, so first this guy is going to dominate. M2G is going to dominate. So M2 is going to fall and faster. But then because the spring force gets larger and larger, it tries to slow down the system. So the tension is going to get larger and larger. And then it's going to be greater than M2, so it's going to decelerate. Okay? So if you want to draw the speed of M2, so you should get something like this. Okay? Maybe not exactly the same shape, but that's the trend, right? That's a tendency. So this is going to be the velocity of M2 start from 0, gets to some maximum value at some point, and then it's going to drop to 0. So that's why the problem says it's going to fall a distance 0.3 meters before coming to a stop. So at some point, say here, M2 is going to stop. Not the ground. Before it hits the ground, okay, it's not because it hits the ground it stops. It's because of these forces, the interactions of these forces here, okay. So then this is a rather complicated process, right? Even if you look at the graph I just drew for the velocity, right? So nothing's constant, even the acceleration is not a constant. So you can't just solve it using like, and if you really want to solve it in using Newton's laws and kinematic equations, you even need to isolate M1 and isolate M2. That's going to be a lot of work, okay? But then the easy way is to use conservation of energy, right? Conservation of energy, I don't care how complicated the process is. Let's pick an initial and final point. Set up all these values, initial and final. Find the work done in this process between the initial and final. Then rearrange this equation, okay? I just work with this whole equation, okay? So let's see. If I want to do that, I'm going to set up this data left-hand side and right-hand side. Left-hand side is always easy to set up, right? You just write down every term using the definition, final minus initial. So let's do that. So I will have, this is M1, and then do the same thing for M2. Now, gravitational potential energy, you will still use the definition M1 now M2 right? So okay, I finished the first two changes. The elastic potential, there is a spring, so you will have, let's just use the definition. I don't even need the detail from the problem. And that's going to be equal to all the external work. Okay? So again, the left-hand side looks scary because, as I said, you're going to write delta K, delta H for every object. So if you have many objects in the system, you will get many terms, but every term has a definition. And in this class, we usually get many zeros, so don't be scared by the left-hand side. We will get a lot of zeros in this question. Okay. So that's the terms on the left-hand side. 10 terms, don't be scared. What about the right-hand side? The right-hand side, let's take a look at the forces on all these, on each object, so I know how many terms I need to calculate on the left-hand side. Take a look at M2, because there are only two forces. Gravity, you never worry about it, right? Because it doesn't go to the right-hand side. Tension, oh, again, this is a whole system. This is my system. Tension inside my system. I don't need to calculate that on the right-hand side. It is doing work on M2. It is, but it's not considered external work. It's not from the outside. Okay, so nothing I need to calculate for M2 on the right-hand side. What about M1? Okay, let's take a look at every force. This guy, gravity, no, inside my system. Tension, inside my system. Normal force, okay, I've done that many times. If I draw the displacement for M1, they're going to make a 90-degree angle. So the normal force doesn't do work either. It is from the outside, but the work that it does is 0. spring force, you still have these two spring force in my system because I have already defined elastic potential energy. So the only work I need to calculate in this question is still going to be the work done by friction force, right? And that's going to be friction force times displacement times cosine theta. And we have done that before. This is very similar to a question we solved, right? So, okay, so the only work I need to calculate on the right-hand side still going to be the work done by friction. And then the work done by friction is going to be the force, displacement, cosine theta. Cosine theta is going to be the angle between the force, which is in that direction, and the displacement in this direction, so it's going to be 180. We already done that before. Displacement, well, if the problem says the M2 is going to fall 0.3 meters before coming to a stop, right? So I'm going to call this the initial point. This is the final point, okay? It's going to start from rest. So the velocity is going to change, very complicated, it's going to go up and go down, but this is when it stops, okay? After this point, it may still go up or go down, doesn't matter. I'm not interested in that. So, or it's just going to stay here, but that's fine. I'm just going to use this point as the final point. So if this is the initial point and the final point is going to fall 0.3 meters from the initial to the final, then the displacement for M1 is going to be 0.3, right? Because M2 and M1, they're connected. So M2 and M1, they always travel the same distance in the same amount of time. They will have the same displacement, the distance, and then the speed, acceleration, but the direction can be different. But these values are going to be the same, right? Okay, so I know this, and the friction force, I know how to calculate that. It's going to be mu k times normal force, and in this case I know normal force equals gravity, not because I remembered that, it's because I drew this Freiberg diagram. I realized in y direction m1g and normal force must cancel, okay? I don't need to remember shortcuts in physics. Okay, so I'm good on the right hand side. I have all the numbers I need on the right hand side. I'm not going to do it now, okay? Again, I always work with symbols first. I'm going to plug numbers at the end because I may cancel some symbols in this process, okay? So all I need to do now, let's worry about the left hand side. Okay, I'm going to leave right hand side there. Final initial speed of the M1. What is the initial speed of M1? Well, okay, the problem says the M2 is going to release from rest. So everything is going to be released from rest. Initial speed is 0. Now, what is the final point? Well, I picked the final point when M2 comes to a stop. Okay, right at that second, that very second. So the final speed of M2 is going to be 0. Then the final speed of M1 is going to be 0. They have the same speed always, right? Because they're connected. So right at that point, the speed of M2 becomes 0. So the speed of M1 is going to also become a 0 right at that second. Okay? So they have two zeros. And these two guys, they're also going to be zeros, right? Because they will have the same initial, same final. Isn't it nice? We already got rid of 4 terms. So there's no data k you need to calculate, right? Is the kinetic energy changing in this process? Yes. Right? The kinetic energy is pretty much going to change this way as well, right? It's going to increase and decrease to 0, but I don't care, right? I only need to find out in the initial values, so I subtract them. And in this case, I get 0 minus 0, 0 minus 0. Very nice. Now, these two terms, take a look at these two terms. M1 is not moving in vertical direction. It's only moving in the horizontal direction. So I don't need to know these two heights. I don't even need the number. I know these two heights, they're going to be the same. There's no change in the height of this M1. Okay, it's very nice. You see that I already crossed out 6 terms. Take a look at M2. So M2 is moving down. So M2 does have a final height and initial height. So again, you're going to pick a 0 reference. In this case, why don't we pick the final height of M2 0? So the lower point is 0, the initial point is going to be 0.3 meters, right? So I don't have a negative signs, okay? I know people are afraid of negative sign, but it doesn't matter, right? You can also assume, say, I call initial height 0, then the final height you plug in is going to be negative 0.3 meters, right? Because it's lower than that. But the difference is always going to say, the difference is always unique, okay? It doesn't depend on the 0 reference. So, okay, so if I call the final height of M2 0, that's another 0. So I only have one term left in this after the first 8 terms, right? Now, what about the spring? The spring, okay, you only looked at the spring. What is the initial displacement of the spring? Well, the problem says when the spring is unstretched, M2 is released from rest. Okay, so delta xi is 0. Because initially it's not stretched or compressed, the displacement is 0. The final displacement, yes, it will have some final displacement because when M2 falls, M1 moves to the right, it's going to stretch this spring. So, but delta xf is also going to be equal to this number. So the initial height of M2, the displacement for M1, and the displacement for the spring, they're going to be the same number because they're connected. They always move the same distance, right? So you know this guy. So now let's put everything together. You see that we started with 10 terms on the left. We're left only with 2 terms, only 2, because we got 8 zeros. Now the work done by friction is going to be the force times the displacement times cosine 180. All right. Now you see that you know all the numbers except for mu k, right? And remember this H2i, this displacement for the spring, and the displacement for the M1, they are all the same number, right? They're all the same number. So you know all the numbers. You see that, and this equation is very easy to solve if you just want to find mu k. You just divide both sides by this factor. Okay, now you can pause the video and finish the algebra, okay? All right, if you do the algebra, what do you get? You will get mu k is just going to be this whole thing plus 1/2 k delta xf squared over m1g displacement of m1 cosine 180. Okay, you have all the numbers. Remember, these 3 numbers, they're the same. They're the same. They're all 0.3 meters, right? You plug all the numbers in. What is your answer? My answer is 0.55. And no unit, right? Because this is the coefficient of kinetic friction. There's no unit. Okay? So this is this question, okay? All right, so we have finished all the questions on conservation of energy. So the last thing we want to discuss in this part is the power. I hope everyone is familiar with this concept, right? If you want to buy a light bulb in a market, you definitely need to know the rated power. You don't want to buy a wrong one, right? What is the definition of power? Okay, power is defined as the time rate of transfer of energy or doing work. So if some energy is being transferred or something is doing work, okay, you can use this power to describe how fast the energy is being transferred or how fast the work is being done. Okay, why do we define that? Because it's useful, right? For a light bulb, it tells you the brightness, right? A light bulb with a higher power, it's going to be brighter than a light bulb with a lower power. So that's why. So this power is actually pretty much like the speed, right? Why do we define speed? Well, because I can use speed to describe how fast something is moving. It's useful in real life, so that's why I define that. So power is also useful in real life, so we can define it as changing energy divided by changing time in the process, or if something doing work, I would just define it as work divided by time. But work and energy, they're equivalent, right? So this is the same unit. And the unit is going to be joules per second. And we do have a new name for it. We call it watt. Okay? So watt is the SI unit of power, or joules per second if you like. So you should be careful. This W, we use the same symbol for watt, the unit of power, and the W, this is the work. Okay? So they're two different things, but we use the same symbol. Unfortunately, we do this a lot in physics because we don't have so many letters. Okay? But just don't confuse them with each other. And of course, the instantaneous power, you just take the derivative of the energy or work with respect to time. Now I want you to take a look at the question on slide 13. Let's take a look at this question. Let's practice this power definition. An elevator motor lifts, elevator again, lifts the 1500 kilogram elevator at a constant speed of 3 meters per second. What is the power supplied by the motor? Okay, so the motor is lifting the elevator. Let's see. So the elevator has gravity down, and the motor has a force up. Right? We have seen this when we defined the when we was defining the gravitational potential energy. Right? So the motor is doing work. Right? The motor is doing work on this elevator, so I can do this. If I want to find the power, I'm just going to do work divided by time. That's how I'm going to find the power of the motor in this process. And then in order to find the work, okay, what do? I would just use the definition of work. Force times displacement times cosine theta divided by time. Now let's see, if I have all the numbers, I'm just going to plug numbers in, right? The force on motor, I don't know, but the problem says it's lifting the elevator at a constant speed. Okay, every time I see constant speed, constant velocity, that means the net force must be 0, because that's Newton's laws. Okay, so in this case, this guy, I don't know the number, but it must be equal to mg in this question, because the question says it's moving at a constant speed. So, okay, at least I know one thing. The value of the motor force is going to be equal to gravity, right? I'm still calculating the power of the motor. I'm not calculating the power of the gravity. But I realize the force is going to be equal. And what is the angle between the force and displacement? Well, if it's lifting this elevator, the elevator is also going up. So the angle between them is going to be 0. Cosine 0 is 1, so that's nice. Now, okay, I can find the mass times 9.8 because that mass is given. But I don't have the displacement and time. I only have the speed. Okay? So how do I find these two numbers? Well, in this case, you don't need to find these two numbers. Okay? Because if you put them together, what do you get? Cosine 0 is 1, so I don't need to worry about it. This is just going to be the speed of this elevator. So, because this is displacement over time. Displacement over time, that's speed or velocity. So at the end, you see that I rearrange this equation. I actually can calculate power only use gravity and the velocity of the motor. Right? Again, is this something I need to remember? No. You don't need to remember this, right? One thing we learned in this question is this. I'm going to manipulate this equation using the laws and theories I learned. So if I want to know two numbers and I don't know them, maybe I can put them together to see if they are equal to another variable, another value I have in the problem. That's the lesson we're learning, right? You do need to learn some skills. You do need to gain some experience. That's why we are practicing. But you don't need to remember some like this conclusion, this shortcut. So next time I see a problem like this, I'm just going to go ahead and write down P equals mgv and plug numbers in. You don't even know if this is going to be true for another problem you see, right? But the definition is always true. The work definition is always true. The math is always true. You just do the math, okay? That's what we learn. Okay, so now if you plug numbers in, what is the power you got? The power I got, it's going to be 44100 watts. Okay, so that's this question. Now let's take a look at the next question. How much energy is consumed by a 1.4 kilowatt hair dryer used for 2 minutes? Okay, so in this question, it's just rearrange this equation to get the energy, right? Because if you know the power, you know the time, how do you find the energy? You rearrange that, you just get, this is pretty much like if you rearrange the speed equation, you get distance equals speed times time, right? So that's the same idea. You just need to make sure that everything is in SI units, right? So kilowatts, you're going to convert it to watts. 2 minutes, you can't just say 2 minutes is the time, right? You need to convert that to seconds, okay? So once you have done the conversions, you can find energy consumed by this hair dryer, okay? So what is your number? So first of all, you're going to convert the power to watts. That's the 1400, right? Time converted to seconds. The second is the SI unit. What is the number you got? 168,000 joules. Okay, so for hair dryer, right, which is very common, right? 2 minutes, you use a hair dryer for 2 minutes, you're gonna use a huge number of joules. Okay, so actually joules and watts, take a look at the last slide. They are very small units when we use that in electricity consumption. It's very easy for you to use like 1,000,000 joules or something like that. So don't be afraid of that. That's just because these units are too small when it comes to electricity consumption. So that's why electric companies then prefer to use kilowatt and kilowatt hours for power and energy. Kilowatt, it's easy to understand, right? That's just 1,000 watts. Kilowatt hour is another unit for energy because if you take a look at kilowatt hour, right? Kilowatt hour is just a product of these two units, which is the power and the time. If you multiply power and time, you actually get energy. So kilowatt hour is a unit of energy, not power, okay? So don't make that mistake. And you can convert it to joules if you want to convert the energy in kilowatt hours or joules. And you don't need the people to give you the conversion, okay? If you understand this unit is just kilowatt times hour. All you need to do, if I want to convert it to SI units, I'm just gonna convert both of these two units to SI units. So kilowatt equals 1,000 watts, and 1 hour equals how many seconds? You're gonna convert it to seconds, right? And then once you have done that, you multiply all the numbers, you will get this, right? And then at the end, you have watt times time. So that's power times time, watt times seconds, SI units. So you will get the unit for, your SI unit for energy at the end, okay? So 1 kilowatt hour equals so many joules. So if you take a look at the electric bill you receive every month, okay, you can see the units, okay? In the electric bill, it's kilowatt hour. They're not gonna bill you in joules, they bill you in kilowatt hours because, again, as I said, if they use joules, you're gonna see a huge number, okay? Like millions or tens of millions or hundreds of millions, okay? So it's gonna freak out. People are always freaked out by large numbers, okay? Okay? So that's why they always bill us in kilowatt hours, and you can see the rate is like 50 cents per kilowatt hour or something, and then multiply that by the kilowatt hours you have used. That's your bill. Okay? I'm gonna stop here for this video.